next session, we have a fascinating interview with Professor Anita Sengupta. She's been a veteran of the space program. Her doctoral research focused on developing the ion engines that powered the Dawn spacecraft to the main asteroid belt. She's been a key part of the designing the entry descent landing systems for the Curiosity rover atop Mars. And she also led the development of the cold atom lab that currently lives atop the International Space Station. Post this, she continued to get senior positions and become senior vice president of systems engineering at Virgin Hyperloop. Today, she dons multiple hats, not only as a research associate professor at the University of Southern California, but also as a professional public speaker and a STEM outreach advocate, all the while successfully running her company, Aerospace Experience Technologies. It's a true pleasure having you with us, Professor, and thank you so much for taking out time to speak with us today.
Oh, good evening. Nice to meet you as well. Happy to be here.
So I'm going to ask you some questions, and we have audience members that are tuning in not only in the webinar, but also through a lot of different other platforms and social media. So I'll be moderating questions from all of these sources and looking forward to getting your insights.
Sounds
As
good.
we just, as we just learned, your experience and credentials are not only storied and impressive, they're also very diverse. Could you tell us a little bit more about your career trajectory and what inspired you to make all of these changes at different points?
Sure. So my background is all aerospace engineering, and my father actually was a mechanical engineer, PhD mechanical engineer. So I always had him as an example in terms of what an engineer could do, and specifically how an engineer can solve problems. So I found that very centering and inspirational. I have always loved space exploration, whether that's from the space shuttle when I was a little kid to science fiction, which I still love to the present day. So I knew as a career choice, I wanted to be involved in the space program. And the best way to do that, obviously, is to become a scientist or an engineer. And I chose the aerospace engineering path. And throughout my career, I was given, or I found new unique opportunities, and I decided to take them. And that's the reason why I moved around quite a bit in terms of what I focused on and specialized in throughout my career in the space program. But after working for NASA, for almost 20 years, I decided it was time for me to go out on my own from the entrepreneurial side of things. And now I have, I founded my own electric aviation company. And I also wanted to do more to help students and young people directly. So I can do that as a professor, both by teaching as well as by having research projects that engage students.
And your focus has focused not only on just space exploration, but also on more terrestrial applications. For example, with the Virgin Hyperloop and what you are doing right now with ASX. What was the motivation for making that switch from the outer cosmos to perhaps a more terrestrial?
So in general, I wanted to solve challenges that were a little bit closer to home, because space exploration is it's exciting and it's fascinating, but it doesn't necessarily solve any of the challenges that we have here at home. So when I was given the opportunity to have a leadership role, an executive role at a green transportation technology company, I felt like that was a really wonderful opportunity to expand my abilities as an engineer in the area of green transportation and actually my abilities as a space engineer to improve on the design of something which was very complicated, but for terrestrial uses. I also like the idea of, as you progress through your career, taking on more leadership roles, specifically as women, and specifically of people, at least in the United States, that belongs to an underrepresented group. So for me, one of the ways to do that was to enter the private sector and also to become an entrepreneur. So, both to further solving challenges that we have here at home, whether that's in India or in the United States, we all have the challenge of climate change. That's pretty much why.
That's actually a very fascinating insight into a very long career. Thank you so much for sharing that with us. And throughout your career, you've led system designs teams for multiple projects. Perhaps one of the most well-known of those is the Curiosity rover and the entry descent landing gear for that. Could you tell us a little bit more about the Curiosity mission and the design process and the challenges you faced during it?
Sure. So the Curiosity rover is part of the Mars Science Laboratory mission, and it was to send a rover to the surface of Mars to conduct a variety of different science experiments focused on understanding whether or not the planet could have once supported life, or even if it's still supporting life to the present day. And the way you do that with a suite of different instruments in terms of understanding the composition of the rocks and the soil, understanding the radiation environment on the surface of Mars, understanding the weather patterns of Mars. But as the engineering team, you could either have been involved in the rover itself, the design of the instruments, or the entry, descent, and landing system that got the rover safely to the ground. It has been done before, sending something to land on the surface of Mars, and it's been done successfully, but this was the largest rover ever sent, and it was being sent to a much more specific location that the science community wanted. So it required the design of a more complex, more precise landing system. And so the discipline associated with that is entry, descent, and landing through a planetary atmosphere. And so there are many different phases to the mission, but the primary job of that phase of the mission is to slow the vehicle down. So the rover is encapsulated in something that kind of looks like a strange looking a bowl, for lack of a better term. And that's done specifically to generate a lot of aerodynamic drag as it descends through the atmosphere. And there are different technologies that are used to slow it down. The first one is a heat shield, which is at the front of the entry vehicle, and that slows it down from supersonic speeds, from 20,000 kilometers per hour down to around 1,000 kilometers per hour. And the next technology is an aerodynamic decelerator, a parachute, which was the portion of the mission that I worked on, which slows it down from about 1,000 miles an hour down to around 250 miles an hour. And then the last portion of the descent is done on retro rockets. I also worked on that portion of the mission, which slows it down to basically a few miles per hour. And so that entire purpose is to sort of target it towards its landing site, keep the rover safe inside of it, but to ultimately slow it down. And all of that has to be done autonomously, which is the reason why it's very complicated, because the distance between Earth and Mars is too far to be able to sort of automatically remotely control a vehicle like that.
Considering the various moving parts and dynamics involved, I think it is amazing how precise the landing happened to the intended site.
Yeah, and
And
that's where engineering really comes in, because you can't actually test that out ahead of time. So all the terrestrial applications I'm working on now, you can actually build an aircraft and fly it and make sure everything goes as intended, in smaller scales or in remote environments. But for something where you're sending to Mars, you can never actually do that. And the environment on Earth is so different from Mars in terms of the gravity, in terms of the atmospheric properties, that even if you do a test, it's actually not a very valid test, because it changes the performance of all the different systems involved. And it's also a very expensive test. So most of that has to be done through a series of very complex simulations or tests in a subscale environment, which represent a given phase of that entry, descent, and landing. And that's what makes it so complicated. But because now you've developed this physics-based understanding for how everything is going to work and how it works together, you're able to predict the performance and do it quite accurately, which is how Curiosity worked this first time around, and it worked really well. And as a result, the Perseverance mission coming up is basically a build to print of the Curiosity entry, descent, and landing mission. So now that one has a much higher chance of success because it's been done before.
that's really interesting to know. And that was also one of the largest questions that we have been getting, that in the absence of actual field tests, how are all of these systems designed and controlled?
Yeah,
Another
you can do some field tests. It's just that you can't do it in the exact same environments. You have to pick certain things to check. So in example of the parachute, although you can't test it in the correct speed supersonically, you can test it subsonically in a higher density atmosphere to get the same total load on the structure.
And I'm assuming that the engineers also build in robust safety mechanisms in case things do not go exactly to plan. How are these designed?
So in fact, you can't build in redundancy. So the way that might typically done for a terrestrial application is that you would have an extra motor or an extra battery. In the case of an entry, descent, and landing system, you can't do that because there isn't enough mass, because the mass has been allocated towards something else and there isn't enough space. So ultimately, the entry, descent, and landing system for Curiosity had a heat shield on it with a maximum diameter of 4.5 meters, which couldn't be exceeded because it wouldn't fit inside the launch vehicle. So you couldn't have added things because it wouldn't have fit and it would have been too much mass, which would have changed the entry performance. So instead what you do is you add in margin to the design and the areas that need it. So sometimes you might add in structural margin. So you expect to see a certain load and then you add 10, 25, 30, 50% margin on top of that, depending upon how well you understand the load that you're going to experience. And then sometimes you might add in margin in terms of having the ability to have more memory or more hard drive space, but there are different ways that you can add in margin. And another important one in the context of entry, descent, and landing is thermal margin. And for a EDL, how much altitude margin you have and timeline margin, which is very, very thin and slim.
Wow, that is almost like an action film. Just how many dynamic parts and variables need to be thought of, and it is amazing how our teams of engineers predict things so far into the process. Your next major project actually was the coal atom lab at the International Space Station, which I assume would be a very different design process from the Curiosity rover. Could you tell us a little
Yes.
bit about that?
Sure. So it's very different in that it was an instrument, a science experiment. So now instead of the goal of working with the teams of scientists, of geologists, ultimately who wanted to understand the surface of Mars, I worked with a team of atomic physicists who wanted to understand the nature of the atom. So the challenge became a much smaller in size because it was an instrument, the size of, basically a refrigerator, a small refrigerator, but became a lot more precise in terms of the way the system had to be designed because it was a laser optical system which had very precise alignments on the order of microns.
I see. Uh, we can pivot a little bit back to Mars because we have the privilege of having such an expert with us. And a question that seems to come in a lot is what are your thoughts about the increasing interest in Mars exploration? Not only from government entities, but also private entities all over the world.
I think it's great. I think that when there is interest beyond just the government side, that's kind of the ultimate goal. So the government will invest in something to generate an interest across the board, across different industrial sectors. So then people from those sectors can take over and continue that investment. So I think we've seen that with sort of commercial access to space, with now the fact that we have SpaceX and Boeing and Blue Origin coming up with ways to basically purely as business opportunities to explore space. So I think we're also seeing that with the moon, and we also will see that with Mars. The challenge with going to the moon and going to Mars is that it does cost a lot of money, so it's difficult for a single entity to carry out one of those projects financially, unless the person, was ridiculously wealthy, such as but in general, that kind of model isn't a good model because then it's only what he wants, not what's best for a whole variety of people and sectors and things like that. So right now we still see Mars exploration and lunar exploration being a sort of a hybrid effort between the government and other companies. And Mars, because now that we're having an administration change in the United States, will probably become more of a focus, and the moon will probably become less of a focus, which I personally am a fan of because I see us as a spacefaring society. We need to get further away from Earth. We need to do something that we haven't done before. We've already been to the moon. So I think going to Mars is the next best strategy for human space exploration to hopefully set up permanent colonies on the surface.
And is that something you anticipate having in perhaps our lifetimes? A manned mission to Mars?
I do. I definitely think it will happen in our lifetimes. Whether or not it will, whether or not we'll be starting up sort of a colonization process, perhaps not. But I think we will see the first people either orbiting Mars or landing on the surface in our lifetimes. There are many technologies that have to yet be developed because the ones that I spoke about before were developed in the context of robotic missions. They don't have high enough reliability to send people there, and the mass that has to be sent to the surface is much larger for a human mission compared to a robotic mission by an order of magnitude. So there's a lot of work that has to be done over the next few decades to make that happen, but it's absolutely feasible, and it really is only limited by people's imagination and funding.
You also mentioned that we are a spacefaring society, and we want to move more and more further away from our planet. That comes with a lot of increased space exploration. And do you think space exploration, the way we are going about it now, is sustainable? Is this something that we can keep up as a society for a long time, or do we need to move towards perhaps more greener space technology?
So I don't think it's sustainable, absolutely not. And I think we need to shift our mindset from going back and forth on journeys to low Earth orbit to actually becoming a spacefaring society. So we have people who live permanently in space or people who live permanently on the surface of Mars, and they're not going back and forth every couple of months, right? So that way you reduce the overall carbon footprint, and then you're basically expanding, right? You're moving out to this new horizon, to this new adventure. Now, the good news is that hydrogen is oftentimes used as a propellant of choice, like hydrogen and oxygen would form. And that is environmentally friendly in terms of the byproduct, of course, being just water vapor. But hydrogen has to be produced. Is that hydrogen produced using means that are using hydrocarbons? That's obviously not environmentally friendly. Or is it produced in an environmentally friendly way? So we have to actually think about all the way back to the beginning. How is the energy? How are the materials being produced? What is the carbon footprint of that here on Earth? So one other strategy for a spacefaring society is that you don't make everything here on the surface of the Earth. You make it out in space. You make it on the surface of the moon. You make it at mining colonies on asteroids, and then you actually have in-space manufacturing, so you don't have that carbon footprint for these technologies on the surface of the Earth. So we have to have a paradigm shift, which is to truly become an off-world society to reduce the carbon footprint of space exploration.
And is this something that you see playing out in the near future? Maybe like central
I
space.
That's a tough one. So most of it is related to investment, like how much money is it going to take? So it's always completely feasible from an engineering perspective. It's just a matter of getting people together and developing those technologies, but having the money and the time to do it. So I think it's largely an investment by governments as well as the private sector. So the more the private sector can find a business case for space exploration, whatever that happens to be, that will help. But largely it has to be funded by governments working with those private industries, and then a new ecosystem will develop. So I think we're probably several decades away from that. We see it in its early stages, obviously, with communications networks, with weather monitoring satellites. Hopefully we'll start to see in-space power systems, and those are the beginnings of setting up that in-space infrastructure that we so much benefit from today, right, in the context of communications. So it's really an investment that has to be made with that mindset from governments around the world working together. It can't just be NASA, it can't just be ESA, it can't just be ISRO. They have to work together, pool their resources, pool their expertise, and then it can happen much faster.
It's really comforting to know that there is a little bit more interest in building off-world systems. Particularly, as you said, it has to be a more combined effort. But there do seem to be some sort of questions about the ethics of building off-world systems that are coming up. Where people say that we haven't completely ruled out life on Moon or Mars, and should we be taking Earth-based materials to these places? What are your opinions
Yeah,
about
it's a great question. And what does exist today is a planetary protection treaty. So all of the space agencies around the world agree to certain guidelines that if you are going to send something to a planet that has, or a celestial body that may have life forms on it in some way, you have to make great effort to ensure that your spacecraft has been cleaned and has had bacteria and bacterial spores removed from it, or at least destroyed by basically heating it up to temperature. So that is something which is already done. So whenever there's a rover that lands on the surface of Mars, or one that might land on the surface of Europa, it has been subject to these planetary protection protocols. Now, when you do a paradigm shift and you actually send people there, we're obviously our own ecosystem with the bacteria and viruses that live within us. So that is a question that has to be answered as a global society. It's not a question just for scientists to answer. It's certainly not a question just for politicians to answer. It's a global conversation that has to be had almost with a venue like the UN to say, do we want to do this? Are we ready to do this? And when we get there, are we going to limit our exposure to only a certain region and do as much as we can to prevent the amount of bacteria that we might transmit to the surfaces on Mars? But it is something that has to be tackled before we get there, well before we get there, in this sort of global conversation as to what the right thing to do is. And I would say that it's really tough, because if you take a hard stance on not wanting to damage another potential ecosystem that might exist, then obviously it's a terrible thing to go bring people there and to bring their own microbiomes there. But I think the likelihood of that being present on the surface of Mars, for example, is very, very low because we've interrogated the surface with a variety of different missions. So if there are microorganisms living on Mars, they most likely live in the subsurface. But I would probably be in the camp that says it's okay as long as we've worked out what the protocols are ahead of time and we do our best to minimize that environmental impact. Okay. That being said, though, we have so much more that we need to do here at home to address our environmental impact first. So once we get that figured out, then I think we can start tackling this problem. So I wouldn't want this to be a distraction from the primary problem, which is to reduce our carbon footprint here at home.
These questions seem to come up a lot when we try to, like, a certain camp of people do try to think of Mars as a do-over planet, where once we're done destroying our ecosystems on Earth, we can just sort of transport everybody to Mars and begin again. Now, that seems very science fiction-y, but do you think it's as science fiction as it appears to be, or could there be any sense of reality for it?
Well, I think it would be for a very small percentage of beings. So I think we'll never get up to the 8, 9, 10 billion where we're headed and transport them elsewhere. So if that did happen, it would have been catastrophic here on Earth. The majority of Earthlings would have perished, sadly. Only very few would go on. So I don't think that that's even a future worth thinking about, because we know that climate change is solvable, and we need to do that now here at home and not think these alternative science fiction scenarios as a solution, because they're not. Their aspirational goal for us as a people, once we've solved our problems here at home and stopped fighting with each other, for example, to go off and things and explore our solar system and explore our universe, but we have to be sound in our judgment and in the way that we conduct ourselves here on our home planet, because there is nowhere else in the solar system, there is nowhere else that we know about in the close by portion of the Milky Way galaxy that will be a home like Earth is to us.
That sounds fair, and perhaps should throw caution to the people who try to think of it this way. Since you are an expert in landing and entry descent into Mars, our audience members want to ask that what could be the potential challenges on doing the same for planets like Jupiter or Neptune, perhaps further out in the solar system.
So there are two different ways that you do entry, descent, and landing. One where you have a planetary atmosphere, a thick planetary atmosphere, like Mars is relatively good. Obviously Earth, Venus is very, very thick, but there are many planetary bodies that don't have an atmosphere. So they use a different approach. So the approach that was used for landing on the moon is more similar to the approach that would be used for landing on the surface of Europa, for example. And in the context of Jupiter, where there isn't really a surface to land on, you would really just sort of like be passing through with an probe like Galileo did, but extremely complicated entry conditions because of the velocity that you're coming with. In terms of the Jovian system, or the Jupiter system, it has its own unique challenge of an extreme radiation environment because of high energy particles that are trapped in the magnetic field that Jupiter generates. So that right now is completely toxic to human beings. So that would have to be solved with some kind of radiation shielding technology. For going further out, let's say to Saturn and beyond, the radiation environment is a lot worse than it is at Mars, but it's not as bad as it is at Jupiter. And we have already landed on the surface of Titan, which is one of the moons of the Saturn system. And so once again, that technology exists for robotic spacecraft, but it has to be scaled up to facilitate people landing there. And then when you add in the people mix to it, not only is there radiation, but there's also life support. How are you going to be able to survive on the surface of this world or in orbit around this world for, you know, months or potentially years? You would have to have enough supplies to be able to survive. So there's a lot of challenges involved. We probably should solve the Mars one first, do that, and then move out. But ultimately, beyond Mars, and even including Mars, the big challenge is radiation in the context of human beings.
I see. It's that you're pointing out the challenges for it's not us sitting at home in space exploration. On the same vector note, there's a fascinating video.
The audio is dropping a little bit.
Okay, can you hear me now? Is this better?
Yes, now I can hear you.
Okay. So there's a fascinating video out there about the 7 minutes of terror when you were trying to land Curiosity on the surface of the planet. And some of our audience members would like to know exactly what was going on through your head and what were you and the team thinking during those minutes.
Well, I think the odd part about it is that there's a time delay. So when you are getting the telemetry data back from the spacecraft or back from the entry system, it's already happened. So for me, I think focused on like, oh, this is so weird because whatever's happened has already happened. It's already landed or crashed on the surface, and we're just seeing the historical record of what I was certainly nervous. I was more nervous about other portions of the mission than the parachute, for example, because I knew so much about it. And I spent so many years working on it. So I was more worried, like, you know, once the heat shield was successful, how was the sky crane going to go? Because I felt like that was maybe the higher risk portion because I wasn't as intimately familiar with the guidance navigation control aspect of it. But certainly nervous, but also very excited. And you don't go and work on these types of things because you're afraid that it's not going to work out. You go because you're hoping that it doesn't work out, and it's so exciting and it's a fun journey to get there.
There are some members of our audience who also want to know a little bit more about the parachute. Like, what was it made of, and how did it withstand these extreme conditions during descent?
So parachutes are used for a lot of terrestrial applications as well. You know, people do sport parachuting. They're used for military applications to drop people and cargo. Parachutes are very different in the sense that the atmosphere is so thin that they have to be deployed above the speed of sound supersonically, which means that they have to handle a lot more aerodynamic load because of that high speed. So they're made out of modern materials. The canopy, sort of the soft goods is what it's called, is typically made out of either nylon or polyester, a very strong but lightweight grade. And then there's a structural grid that this canopy material is sewed into, which is made out of Kevlar, which is Kevlar webbing, basically, which is the same material that bulletproof vests are made of. So again, very, very strong, but very lightweight. And it has to be designed in a way so that the load is distributed, even though the environment that you experience on Mars and the supersonic environment, load is not distributed evenly inside the canopy. Sometimes it's distributed unevenly, which means you then have to apply a margin in specific places to be able to get you to a structural network which will survive very harsh loading conditions.
And all of these are tested and designed on Earth in the smaller sub simulations that you were talking about. Say?
So it depends. So we were able to test the parachute at full scale inside a very large wind tunnel, but in a sonic environment to give you the same total load for a sort of uniform pressure distribution. But I also conducted a test program where I made small parachutes and then tested them in a relevant environment inside of a small wind tunnel, which simulated Mars conditions, but a much smaller scale. And then we also conducted a series of computational fluid dynamics simulations and fluid structure interactions to understand kind of what the loading was throughout the canopy to ensure that we had enough margin and that we would get sufficient performance. So you do sort of a combination of both, but our simulations were so sophisticated that we had to run them on supercomputer networks, and they would take weeks just to generate a few data points.
That's interesting to know. Another question that's coming up talks about perhaps the team's attachment to their rovers. This is in context of the fact that there was like a global outpouring of love and sorrow when the Opportunity rover said goodbye in 2019. And the audience members just want to know if that's something that you feel towards Curiosity, or what's the general atmosphere and connections to the missions that you work like at.
Well, I suppose I probably don't feel an emotional connection to the rover just because it is a mechanical device, and you know, I have, you know, pets and things like that, so I have more of an emotional to living life forms. But I think that I have so much respect for the amount of energy and expertise and dedication and devotion that went into the success of these missions, even when they're not successful, that I feel for the people behind them who feel sad when the work that they, you know, spent so many years of their life on either didn't work out or has now come to an end. So I feel my empathy is towards the people behind the rover, as compared to the rover itself. Now, I didn't work on the prior missions. I only worked on Curiosity, so I don't have that connection to the prior rover. So maybe my tune will change when Curiosity goes. But to this point, I have always focused on sort of like the human beings and the idea behind the mission. But in general, it's almost never bittersweet because you generate so much amazing scientific data, and then you get to use that for the next mission, like Perseverance, for example, so it lives on in its reincarnation.
That's it's It was really fascinating also to see how the global community of space enthusiasts perhaps get attached to the mechanical rover itself. And I think it's very indicative of the global interest in Mars exploration, from amateurs to scientists to obviously engineers like yourself who work at in the actual constructions of it. Some of our audience members also want to know how exactly do the different teams communicate and interact with each other?
It is very difficult to manage any team, and it's very, very difficult to manage a highly multidisciplinary team. And so there is a field of engineering called systems engineering, which is the key to NASA's success in both human exploration as well as robotic exploration. And without systems engineering, you would never be able to pull off a mission as complicated as Curiosity. And so most other fields within engineering or within software development do not use system engineering. I don't know how they survive because I'm a system engineering expert, but what it is, the system engineer program starts from the very beginning of the mission. They get the requirements from the customer, whether that's like science customer or your government customer who's giving you money, to figure out what is it that you want this mission to do. And then they decompose those requirements into lower level requirements until eventually they get all the way down to requirements at the component level. And then you make sure that you have a design which meets those requirements and that you have a way to verify that you meet those requirements, all the way at the lowest component level, all the way up at the system level. And because you go through that process of breaking the problem down and making sure that it works at every stage, all of a sudden now you also have a way to communicate, because now you have system engineers who are constantly monitoring those interfaces at a lower level, at a higher level, who are verifying independently that people have a design that meets the requirements, that their test program actually goes off and generates the data that shows that they will work at that level or at the higher. And it works incredibly well. Most other disciplines of engineering, specifically the automotive sector, and in some ways, even the aviation sector, don't have that. And that's the reason why NASA is able to do what it does so successfully for these really complicated missions, but you have other things simple as a car that don't work that time around.
Thank you for giving us that nice peek in actually what happens behind the scenes. And because these are such complicated projects, I assume that the maintenance for them would also be as complicated, right? For example, the cold atom lab atop the ISS was repaired once by Jessica Meyer and Christina Koch. How do you build in the redundancies and repair mechanisms for these in your systems design and engineering processes?
So for Cold Atom Laboratory was a little bit different because we knew ahead of time that we would have the ability to have upgrades and repairs. So it was designed with that in mind from the very beginning. So part of our system engineering process for Cold Atom Laboratory was to say, we're going to achieve a mission lifetime by having the ability to have on-orbit replaceable units. So we made a decision ahead of time. This could be replaceable, and how would the astronauts go about opening up the instrument, taking out the broken item and putting in a new item, and how to make sure that those interfaces work both physically as well as thermally, as well from a software perspective. So we designed it with that in mind.
I see. Okay. And could you tell us just a little bit more about what the Cold Atom Lab actually does for members of our audience who may perhaps be new to it?
It is a facility which uses a technique called laser cooling to cool atoms down to a temperature where they condense and form something called a Bose-Einstein condensate. So we're using only atoms which are bosons, and we're cooling them down to temperatures basically just above absolute zero. And when bosons get down to that temperature and condense, they take on different behaviors, which are very unique. And by doing this experiment in orbit in a microgravity environment, instead of looking at it for a few milliseconds that you do in the laboratory here on Earth, you can now look at them evolve over a period of many seconds. So we're getting more understanding into the nature of the atom.
I see. Thank you so much for telling us about some of your work during the space exploration program. And now we can move ahead and look a little bit towards your terrestrial work. You're now a research associate professor at the University of Southern California, right? And you've also advocated a lot for working with students and upcoming aeronautics engineers. How, what prompted you to make that change from some place like NASA and JPL to perhaps a more university space?
Well, I am a researcher, I am a technologist, and I think sometimes the way that you can do the most on the research front is to do it in an academic setting or in a small business setting. When you're part of a really large organization, sometimes it's a little bit harder. And if you want to turn something into a product which is accessible to the general public, then you can't really do that in a government organization. You have to do that either in academia or in business environment. And you have the ability to propose to get funding as a professor or as an independent smaller company. That it's much harder to do when you're part of a big organization because you've got thousands of other people and lots of different processes to follow. And the organization may not think that what you're doing is worth the organization spending time on. So it's more about being in the driver's seat of your own unique project as opposed to being part of a very, very big team. So I have loved in my career being part of these enormous teams and leading enormous teams, but
Yeah.
now, like in the second phase of my career, being able to innovate as a researcher and as a technologist, both in the private sector space as well as in the academic space. And now I can reach out and work very, very closely with undergraduate students and graduate students.
These innovations that you're talking about also seems to be the goal for the current company that you head, right? Aerospace Experience Technology. Can you tell us a little bit more about what your aims are as a part of that company?
So I co-founded ASX about 2 years ago. I came in as sort of like a mid-stage co-founder, and that electric vertical takeoff and landing aircraft system. And the reason why I was involved in joining that effort was because I'm a very active pilot and I know that my flying has a large carbon footprint. So I wanted to develop technologies that would facilitate reducing the carbon footprint of aviation. And so the eVTOL space has that as a goal to be emission free, lower noise. But during the course of development, I realized that batteries, which was the technology that everybody is focused on in the space, from the big companies like Boeing to the much smaller companies, are not a good fit for aviation because they're too heavy and they don't have good enough energy density. So several months ago, I actually founded a new company, which is called Hydroplane. And so I realized that the right solution to reducing the carbon footprint of aviation is to shift over to hydrogen fuel cells. So now my focus of my entrepreneurial venture is to develop a hydrogen fuel cell power plant for small aircraft.
I see. And a lot of your work has been in the aviation industry, in the space industry, which are traditionally largely considered male dominated industries. um, as perhaps not a part of the dominant society, how has that informed your experience over the course of your career?
So, I mean, this is a true sentiment that many of my other women colleagues feel. But when you are part of an underrepresented group, whether it's because you're a woman or you're a person of color like me in the United States, you are held to a much more difficult standard. Oftentimes, you're not maybe treated as well as you should be. You may not be listened to. People might speak over you. They have like the mansplaining and the heap-eating happens all the time. So the only way around that is to become so good at what you do, to become such an expert that people have to listen to you and people have to go to you for your advice. And so that has been my solution, is to get as much as I can, to get as much experience as I can, so I can be, a lot better perhaps than my male peers. And as a result, I can be in the driver's seat.
That is definitely advice that I hope I will take forward in my own career. And
And by the way, it's not fair, but at the same time, there are always going to be things in life that aren't fair yet. But when we are successful as women in this field, we help all the women that come next so that their journey won't be as difficult.
yes, fingers crossed that that happens. You've also done a lot of science outreach work as a professional public speaker, and you have some fantastic keynote addresses out there. What prompted you to sort of go down this path?
So I've always had this strategy in my life where if you don't feel comfortable doing something, you really got to go do that thing. So comfortable was with public speaking, and so I started off by speaking to little kids. I participated in this after school program that NASA ran, where you could come in as an expert and talk to like fourth, fifth, and sixth year graders. So they're probably like 9, 10, 11, 12. So teaching rocket science to little kids is very difficult to do. So I figured if I can do that from the communication perspective. So I started off with little kids. And then I expanded to adults, and I joined the Speakers Bureau. And so I got a lot out of it because I got to share stuff that I loved. I got to learn how to be a public speaker. I got to learn how to communicate really difficult subject matter to lay people or to little kids. And it kind of took off from there.
I see. I think that's some of your speeches and some of your public speaking keynotes out there have actually been very inspirational for people wanting to get into aeronautics and aviation. And I was wondering, do you have any message for our young listeners and our young college undergraduate students about how they can pursue a career in astronautics, aerospace, aviation, or even space entrepreneurship?
So I would start off on one level higher, which is whatever you do in your career, it should be something that you want to do, something that you feel passionate about it. If you don't feel passionate about it, you're probably not going to stick around for very long. So don't do something because your friends are doing it, because your parents tell you to do it. You have to do it because you want to do it. And if you don't know what that is yet, then look around, try different things, and hopefully you'll figure it out. And you can do that by volunteering and things like that. Now, in the context space program, if you want to be a part of the space program, if you love space exploration, if you do a really good job in school, you will be almost guaranteed to get a good job in the aerospace sector. So there you want to become, aerospace engineer, mechanical engineer, electrical engineer. Some cases, usually not civil, but there are some ground-based applications where you could make use of that. But I would say mechanical, aerospace, electrical are the right disciplines to get into if you want to be on the engineering side. If you want to be on the science side, then you can be an astrobiologist, you could be a geologist. Those are probably the two primary science fields, or astrophysics and astronomer and things like that. So those are the you can focus your academic career to get you to where you want to go. Now, getting advanced degrees is important and very helpful. So if you want to develop technology or if you want to be a research scientist, then you should go and get your PhD. If you just want to do engineering development of a system and perhaps not be sort of in the lead technologist role, then you could, I would say, just get a master's degree. You don't have to get a PhD. But in general, becoming more educated is a wonderful thing. And many people who are in high level positions of leadership have PhDs as well. So they end up doing research for a while, but then they shift over to more of a leadership management role, and it really helps them in their career. So, and then also make use of internship opportunities, whether those are at your university, another university, a government agency, or an industry, and try and do those every single summer. And if you can, even take a semester off to do one.
Thank you for very wonderful insider and profound advice for our young listeners. Uh, the last 45 minutes have just flown past, and I'm sure we could talk perhaps for hours more. You've had an interestingly fascinating career, and there's a lot for us to learn. But perhaps one last question that I'd like to end this is, what role do you think public engagement platforms like the India Science Festival play in bringing credible science closer to society?
I think it's really important because young people especially, need to understand what it means to have a career in the field. Who are these people? What do they do? How can I be like them? And hearing from them directly is really important. And in the context of space exploration, sometimes people only think, oh, I can be an astronaut, or I want to be an astronaut. An astronaut represents, like, I don't know, maybe 2% of what the space program does. So I don't think that's the right way to focus career, that I can be an astronaut. You should be focused, how can I be an aerospace engineer, a mechanical engineer, a software developer, an astrobiologist, a geologist. So by showing people these different career paths using platforms like this, now a lot more people will be reached, as opposed to the people who are like, I'm going to become a fighter pilot and an astronaut, right? So that's why it's important to give people a realistic path to success and understand how there's multiple paths to those success. So by educating them, by exposing them to experts like myself and others, is the right way to do it.
Thank you so much for your wonderful words, and thank you so much for taking time out to speak with us. I speak on behalf of the team of the entire festival, as well as our audience members, that this has been a fascinating hour of conversation, and your insights and your expertise will certainly help a lot of our young audience.
Oh, thank you. And feel free to follow me on Twitter as well. So I do a lot of space tweets on Twitter.
You can find her Twitter handle in the chat. It's been just put in the chat by one of our moderators. And thank you so much for taking time out with your extremely busy schedule to speak with us. Do you have
Have a
any
good
parting
evening.
words for our audience?
Yeah, I always like to use this phrase, which is the sky is not the limit, it's only the beginning. So go out there, make an impact.